In the last unit, we went over chemical equilibrium and how it can be affected by pressure and temperature and different things like that. We also learned how to go and calculate out the equilibrium composition of a system, using the Kc and also the ice table as well. On this chapter, what I want to do is just go over, first off, an introduction into acids and bases, which a lot of this might just be a review. You might have gone over it already. And then after that, get into acid and base equilibrium. So we'll learn, we'll take some of what we learned in the previous unit and then apply it into this unit. So the first thing I want to do is just go over some of the properties of acids and bases. And some of this you might know just from everyday life. When you encounter acids and bases, for acids they taste sour. So for instance, if you have vinegar, vinegar tastes sour, because of the fact that it's an acid. And also, if you were to use blue litmus paper, you would notice that that blue litmus paper would turn red, if you put it into an acid. As far as bases go, they taste bitter. Which, for example, if you ever got soap in your mouth or shampoo in your mouth, you know that it tastes kind of bitter, and that's because that is a base. It also feels slippery, so that's why, with soaps and everything, they feel slippery, because, again, those are bases. And then if we were to use red litmus paper, within this particular solution, you would notice that the red litmus paper would turn blue. So now let's just go into some of the definitions for acids and bases. Before that though, for the most part, acids and bases are made up of two different ions, the hydrogen ion and also the hydroxide ion. Hydrogen being H+, and we'll also look at a different form as well, and also hydroxide is OH-. Now, the amount of those particular ions will determine whether a solution is acidic, basic, or neutral, depending on how much you have of each one of those. A solution will be acidic if you have a greater number of hydrogen ions than hydroxide ions, so the H+ concentration is higher than the OH, and then you'll have a solution that's basic if you have more OH ions than you do H+ ions. So let's just go over a couple of definitions. Like I said previously, one definition is just basically the Arrhenius definition for an acid and base, which this might be the one that you're most familiar with, which basically says that if you put an acid in water, it will produce an H+, or another way of doing this is to represent it as H3O+, which that is known as the hydronium ion, and I'll show you how that forms when an acid hits water. Now, as far as the base, if base is in water, it will produce an OH- ion, which those are known as hydroxide ions. So that definition is probably the one that you know the most or the best. Another definition, though, is the Bronsted-Lowry definition, which just basically says that an acid is a hydrogen ion donor, meaning it gives up an H+, and then a base is a hydrogen ion acceptor, meaning it gains that H+. So for example, if we were to look at an equation like this, you have your HX, which that is your acid, and what it basically does is it gives up an H, which you can see on the other side, it forms X-, and that H actually reacts with the water, or attaches with the water, to form your H3O+. So because that H3O+ accepts an H, that would be a base. Now, going along with acids and bases, usually on the reactant side of a reaction, you're able to easily determine what's the acid, what's the base. The acid would be the one that starts with an H. A base is the one that has an OH within its formula. So that's easy to be able to figure out. On the other side, though, when it forms a product, it goes and forms what's known as a conjugate, which basically means that it turns into the other type. So for example, if you start off with an acid, it'll turn into a conjugate base. If you start off with a base, it'll turn into a conjugate acid. So what you need to do is figure out which to be able to label which one is which. Which one's the conjugate acid, which one's the conjugate base. And basically the conjugate acid is going to be the base that accepts an H+, so whatever accepts that H+. And then the conjugate base will be the species that actually donated the H+, what forms once that H+ is gone. So let's just go over a couple of examples. This first example, you have HF and H2O on one side, and then you have H3O plus and F minus on the other side. First thing you want to do is figure out on the right side which one's your acids and which one's your bases. Like I said before, your acids will always start with H, so in this case HF would be your acid. And within every single reaction you always have an acid and a base, so H2O in this case would act as the base. So you have your acid, you have your base. Now on the other side, this HF gives up an H, so you form F minus instead. So this would be known as your conjugate base because it gave up an H. Your H3O plus, as you can see, it's just basically H2O, but it gained an H. If it gains an H, that's your conjugate acid. So it's just basically the opposite on the other side. So let's go to the next example. In this case, you have, again, if it starts off with an H, it's your acid, so that's your acid. OH minus would be your base. On the other side, you notice that with the HCO3 minus, it loses an H plus, so it becomes CO3 minus 2, so that becomes your conjugate base. And then the OH minus gains an H to form H2O, so that would be your conjugate acid. So just know that on the other side, on the right side, whatever loses the H is your conjugate base, whichever gains the H is your conjugate acid. Now in this case, you're not given a reaction, so you need to figure out how to determine what the conjugate acid of a particular base is going to be. Before that though, just to show you what I was talking about before, a base is not only something that has an OH in it, it can also be something that has an H on the right side, or the right half of a compound. That's also a base. So NH3 in this case would be a base. So now you want to figure out the conjugate acid, which basically the conjugate acid is going to be the one that has one more H than the base, because it's gaining that H. So if that's the case, NH3 is gaining an H, so it would be NH4, but it's also gaining a positive charge when it gains that H, so it becomes NH4 plus. So that would be the conjugate acid of this. Again, because of the fact that it's gaining an H. And then within this example, you're given an acid, which is HC2H3O2, and then you want to figure out the conjugate base. Conjugate base, again, just to go over it, is always going to be the substance that loses an H. So whatever results after you lose an H. So if you have HC2H3O2, if that loses an H, it becomes C2H3O2, and because you lost a positive charge, you're left over with a negative charge. So that would be your conjugate base in this case. Now, you might wonder why it is that it's that H that you get rid of and not one of these. It's always going to be the H that's the easiest to get rid of. This is a little bit more difficult to be able to get rid of an H that's already attached to other things. With the H in front, that can easily be ionized and be let go. So that's why you get rid of the one in front and not the one within the formula itself.